Hello, geometry students. Mrs. Myers here with you with day 3 of our coordinate geometry proofs. So today we are going to be taking a look at the trapezoid. So first of all, let's just talk about a trapezoid. It is a quadrilateral with at least one pair of opposite sides parallel. If the other pair of opposite sides are not parallel, then it is a general trapezoid. And of course, as we already know, if both pairs of opposite sides are parallel, then it's a special trapezoid referred to as a parallelogram. So we've got our flow chart that we have already seen way back from earlier in the year that I thought it would be a good time to talk about it right now. So we've got ourselves the basic quadrilateral, which, right, you know is just 4 sides, right? Now, there are special types of quadrilaterals called parallelograms, which we know about that, right? And we've already done that on day 1. Then there are more specialized types of parallelograms referred to as rectangles. We already did that on day 1 as well. Then on day 2, we talked about the special type of parallelogram called the rhombus. Okay, and then we also talked about the special type of rectangle rhombus parallelogram called the square. So that all came together, all of those arrows came together there. Now we have another day of coordinate geometry proofs to do that talks about another special type of quadrilateral called the trapezoid. Okay. Now what we want to do though, so even though I'm veering off with the quadrilateral in a different way to get the trapezoid, I'm actually going to arrow back here to parallelograms afterwards because a parallelogram is a special type of trapezoid. Okay, so we kind of have an extension now to this flow chart that we learned about way back in the beginning of the year with this extra piece of information right here called the trapezoid. So first thing, of course, we want to do when we are looking at our example here, okay, is we want to have a sketch going on. So we've got point A, which is -3, -1. Okay, we've got point B, which is -1, +3. Okay, we've got point C, which is 2, 3. And finally, we have point D, which is 4, -1. Okay, so if we connect those, of course we can see, right, it's a quadrilateral. So we've got, let me just fix that a little bit there. So we've got, first thing that we're doing is we are verifying that this is a general trapezoid, but not a parallelogram. Okay, so that was basically what I just talked to you about here, is if we have one pair of opposite sides parallel, but the other pair of opposite sides not parallel, then it's a general trapezoid. If both pairs of opposite sides are parallel, then it would be a parallelogram. So that's what we have to do in this piece right here. Now, afterwards, okay, part B of this is we are going to determine whether it's an isosceles trapezoid. So there's 2 things that we can do to determine if it's an isosceles trapezoid. Okay, we want to go through some terminology here. Okay, for general trapezoids, the parallel sides are called bases. Okay, that's important. And then the non-parallel sides are called the legs. Okay, so I think it's very obvious to see, which pair look parallel and which pair don't look parallel. So these would be your bases and these would be your legs. So one possibility is if the legs of the general trapezoid are congruent, then it would be an isosceles trapezoid. Okay, so A, B, and C, D. Okay, we'll do that here. But the other possibility, so this is an or, you wouldn't have to do both of these things, is if the diagonals are congruent, then it's an isosceles trapezoid as well. So the diagonals are always the ones in the quadrilateral that connect the opposite vertices. That would be AC and BD. Okay, so let's get started proving that it's a general trapezoid and not a parallelogram. So we want to prove that one pair of opposite sides are parallel, the other pair of opposite sides are not parallel. And like I said, by doing this quick little sketch, it's very, very obvious which pair are and which pair aren't. So we're going to, show our work nice and neat and organized. First thing we're going to do is find the slope of side BC. Okay, so again, our slope formula, hopefully you guys remember, is y2 minus y1 over x2 minus x1. All right, and slope of BC, so we'd have the difference of the y's is 3 minus 3. The difference of the x is 2 minus -1. Okay, just make sure you're consistent with the order, although, of course, since you do 3 minus 3 and they're the same, it doesn't really matter which way you subtract those x's. and we get 0 over 3, which anything divided into 0, 0 divided by any number is always 0. So now we're going to compare that to the slope of side AD, which is across from it. Okay, notice how I'm putting my information together and being nice and organized. All right, please do the same for your assignment. So AD, we've got change in y is -1 minus -1, and then change in x would be 4 minus -3. So this is 0 over 1. And that is again 0. So what do I know about these two segments? Because they have the same slopes. Remember, some of you in your work are not showing what this coordinate geometry formula and the value of it tells you, okay, about the segments that you're doing this work with, okay? You're not just showing the calculation of these, slopes or distances or things like that. You're telling me why you did it, what it means to you. So because I got these two slopes to be the same, I know that these two line segments are parallel. So I write that down, and then I write down why I know that they're parallel and it has the same slope. So that is a very, very important thing to do, okay? Don't just show me the work and not tell me that statement and reason from it, okay? So we're going to go on now and do the slope of side AB, right, which is 3 minus -1, for example, for change of y's. And then since I did 3 minus -1, I'm going to go -1 minus -3. So that is now 4 in the numerator, and that's 2 in the denominator, which is only a 2. And I'm going to come over here to the slope of side CD. All right, and that is 3 minus -1 for the change in y's, and 2 minus 4 for the change in x's in the same order. Make sure you're consistent with that. y2 minus y1 over x2 minus x1. So numerator is 4, denominator is -2, and that gives me a -2 slope. Now, be careful, okay? Please reach over 1 if you want to leave them over 1. These slopes are not the same, but they are not negative reciprocals either, okay? There are only two different things that slopes can tell you about line segments. They can tell you if they're parallel or perpendicular. Remember those two P words. Those are the only two things that you can determine from doing slopes. If segments are parallel versus not parallel, and perpendicular versus not perpendicular, okay? So same slopes as parallel, exactly the same. These are not the same slopes, okay? Perpendicular segments have negative reciprocal slopes. So although these are negations of each other, this is a positive slope and this is a negative slope, they're not reciprocals. So all that we can say here is that these are not parallel, okay? And what I'm going to do for not parallel is I'm just going to put the slash through them, and I just write down different slopes, okay? And now, what is my overall conclusion? I don't really have a whole lot of room, but let me squeeze it in here. I would say that ABCD is a general trapezoid, okay, because only one pair of opposite sides are parallel, okay? So that is what you would want to say right there. Anyway, let's keep going, okay? So now we know that it's a general trapezoid, okay? Not a special type of trapezoid called a parallelogram, because I've got one pair of opposite sides parallel, but the other pair are not. So now I want to determine if it's an isosceles trapezoid, okay? One way to do it is if the legs are congruent. So we do not use the slope formula to determine congruency. We use the distance formula, okay? So quick reminder here, distance formula, square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. All right, and I'm first going to apply it with the legs. So the legs are the non-parallel sides, okay? So I go AB without the bar over it. That means I'm going to find the distance of it, square root of, and now I do the x's. So for example, I can go -1 minus -3 quantity squared. And then in the same order, I'd go 3 minus -1 quantity squared. So this is 2 squared and this is 4 squared. All right, so this is 4 and 16. Add that together and it's square root of 20. So we're going to compare that to the length of segment CD. So I do change in x's. So for example, I can go 4 minus 2 quantity squared, and then I would go -1 minus 3 quantity squared. So now I have 2 squared and -4 squared. Okay, remember you're adding the opposite deal there with the subtraction, and you get 4 from 2 squared, and 16 from negative 4 squared. Notice how I kept those parentheses going. Okay, some of you are being careless and dropping those parentheses. So let me just reiterate again that you always keep the parentheses until you are done with the squaring, because otherwise, if you don't keep parentheses and you go negative 4 squared like that and you write 16, now you've made 2 errors. That's wrong because you did not keep the parentheses, and that's wrong because negative 4 squared without the parentheses really means negative 16, okay? So please be very, very careful, all right? Anyway, add those together, that's square root of 20. So now compare these two lengths. They are exactly the same. What does that mean about those two segments, okay? We have to write our statement, okay, and our conclusion as to why we know, what this information told us. So AB is congruent to CD because their lengths are the same, right? Same lengths. Okay, so now that I've determined that, what do we know about trapezoid ABCD? We know it is isosceles, right? So ABCD is an isosceles trapezoid because, use the correct lingo, the legs are congruent, right? These were the non-parallel sides over here that I've now determined were congruent, and that is enough to tell me that this is an isosceles trapezoid. But I have another possible way that I could have done it, and that is to still use a distance formula, but with the diagonals. So AC is a diagonal, BD is a diagonal. So I'm going to come here and go AC's length is equal to, and I'm going to go BD's length is equal to, and I just do the same formula. So AC is, for example, 2 minus negative 3 for change in x, okay, and then it's going to be, if I go 2 minus negative 3, I'm going to go 3 minus negative 1, and that is 5 squared and 4 squared. All right, so this is now 25 and 16 added together, which is square root of 41. So let's see what the length of BD comes up as. So we've got 4 minus negative 1 as the change in x, x2 minus x1, and then in the same order, negative 1 minus 3, okay, would be my change in y's. So add the opposite, that's 5 squared. Add the opposite, that's negative 4 squared. Keep those parentheses. Okay, this is 25, this is 16. Add them together and you get square root of 41. Okay, and we were expecting that because we already know it's isosceles, but now we write down our statement. So what do these equal lengths tell us about segments AC and BD? It tells us that they are congruent segments, and I write same lengths as the reason why I know that they're congruent segments. And then what is my conclusion about my trapezoid? So now I say ABCD is an isosceles trapezoid because the diagonals are congruent. And that is it. Okay, so that is the end of day 3 with coordinate geometry proofs. There is a problem set that goes along with this, and I hope you find that to be an easy problem set. All right, be sure to let me know if you have any questions, concerns. Thank you. Bye.